Picture this. You've been grinding on a bug for 2 hours. You finally nail it. You type git push, lean back, grab your coffee, and 3 minutes later, without touching anything else, your fix is live in production. Tests ran. App was built. It deployed. All by itself. That moment feels like magic. And honestly, it kind of is. But magic has rules. Magic has architecture. What you just witnessed is called a CI/CD pipeline, continuous integration, continuous delivery. And GitHub Actions is the engine underneath it. Not some third-party service you have to wire up separately. It's baked right into GitHub. Your code and your automation live in the same repository. In this chapter, we're going to peel back the curtain on that magic. We're going to trace exactly what happens between the moment you push and the moment your app is live, every trigger, every decision, every machine that spins up and runs your commands. By the end of this chapter, you'll have a complete mental model of how GitHub Actions orchestrates your pipeline from a single Git event all the way to a deployed application. Let's go. Here's the beautiful thing about GitHub Actions: the entire system, no matter how complex the pipeline, is built from exactly 5 concepts. Not 15. Not 50. 5. Think of it like learning the rules of chess. There are only 6 piece types. But the combinations are infinite. GitHub Actions is the same way. 5 primitives, infinite pipelines. Let me give you the golden chain: event, workflow, job, step, runner. An event is what kicks things off. Something happens in your repo. A workflow is the YAML file that says, when that thing happens, do this. A job is a group of related steps that run together on one machine. A step is a single command or pre-built action. And a runner is the virtual machine that actually executes it all. That's the entire mental model. Everything else in GitHub Actions, every advanced feature, every optimization, every trick, is just a variation or an extension of these 5 things. Understand this chain, and you can figure out anything. We'll now zoom into each one in detail. Starting with what sets the whole chain in motion. Imagine GitHub as a massive surveillance system, but for your codebase. Every action you take in a repository, GitHub is watching. Someone pushes code, GitHub sees it. Someone opens a pull request, GitHub sees it. Someone leaves a comment on an issue, creates a tag, schedules a cron job, GitHub sees all of it. Each one of these observations is an event. And an event is the starting gun for your entire automation pipeline. The classic event is the push event. Every time anyone pushes commits to your repository, GitHub captures a webhook payload, a JSON object packed with information about that push. Who pushed? What branch? What commits? What files changed? All of it. This payload is sent to the Actions system. And your workflow file says, when I see a push event, here's what I want you to do. But push is just the beginning. There are over 35 different event types in GitHub Actions. Pull request events. Release events. Issue events. Scheduled events that run on a cron schedule. Manual events triggered from the GitHub UI. You can even trigger one workflow from inside another workflow. Events are the heartbeat of the entire system. Nothing happens without one. So an event has fired. GitHub knows something happened. Now what? Now it looks for the blueprint, the workflow. A workflow is a YAML file that lives in a specific place inside your repository, the .github/workflows/folder. GitHub scans that folder automatically. You don't register it anywhere. You don't tell GitHub it exists. You just put the file there, push it, and GitHub starts using it. A workflow file has 2 main parts. The LANA section, which lists the events that should trigger this workflow. And the jobs section, which defines what to actually do. Here's something powerful: one repository can have multiple workflows. You might have a ci.yml that triggers on every pull request and runs your tests. A deploy.yml that triggers when you merge to main and deploys to production. A securityscan.yml that triggers every night at 2 a.m. A cleanup.yml that triggers when you close an issue. All completely independent. All living in the same folder. Each workflow file is self-contained. It has its own triggers, its own jobs, its own secrets. They don't interfere with each other. And because they live in your repository, they get full version control. You can review changes to your CI/CD pipeline in a pull request just like any other code change. Inside a workflow, you define jobs. A job is a collection of steps that all run together on a single machine. But here's the critical architectural insight that trips up a lot of beginners: every job gets its own fresh virtual machine. Job A and Job B are not running on the same server sharing files. They're running on two completely separate, freshly provisioned VMs. This has a huge implication. If Job A creates a file, Job B cannot see it unless you explicitly use an artifact to pass it between them. Now here's the performance unlock. By default, all jobs in a workflow run in parallel. If you define a test job and a lint job, they both start at the exact same moment, each on their own machine. Your total pipeline time is determined by the slowest job, not the sum of all jobs. But sometimes you need order. You want to run tests before you deploy. That's where the needs keyword comes in. You write needs, test, on your deploy job, and GitHub Actions says, got it, deploy will not start until test finishes. And not just finishes successfully. If the test job fails, the deploy job is automatically skipped. You never ship broken code by accident. This parallel by default, sequential when needed model is what makes GitHub Actions so fast and so safe. We've drilled down through events, workflows, and jobs. Now we reach the actual atomic unit of work, the step. A step is one thing. Either a shell command you write yourself using the run key or a reference to a pre-built action that someone else wrote using the uses key. That's it. That's a step. What makes steps interesting is how they relate to each other. Unlike jobs, steps run in sequence, top to bottom, always, in the order you define them. There's no parallelism within a single job. Step 1 completes, then step 2 starts, then step 3. This predictability is intentional. And here's the key: file system behavior: all steps in a job share the same runner. When step 1 clones your repository, step 2 can immediately run tests on that code. When step 3 builds a Docker image, step 4 can push it. The runner's file system is a shared workspace for the entire job. If any step fails, exits with a non-zero code, the job stops immediately. The remaining steps don't run. This fail-fast behavior protects you from wasting time and resources running subsequent steps when something has already broken. You can override this with continue on error, true on individual steps if you need to. But the default is safety: one failure stops the whole job. Here's a question: how do you clone your repository onto the runner? You could write a bash script. Set up authentication. Handle edge cases for shallow clones, submodules, LFS. That might be 40 lines of fragile shell scripting. Or you write one line, uses, action/checkout at v4. And suddenly all of that complexity is handled by a battle-tested, maintained, open-source action written by GitHub's own team. This is the power of actions. They're prepackaged, reusable automation units. You reference them with uses, and pass parameters with. GitHub downloads and executes them on your runner automatically. Actions come from 3 sources. Official actions maintained by GitHub Live under the actions/namespace, things like checkout, setup node, cache, and upload artifact. Community actions live on the GitHub Marketplace, over 20,000 of them for everything from sending Slack notifications to deploying to AWS. And you can write your own private actions that live in your own repository. One crucial security practice: always pin actions to a specific version tag, like at v4, never at main. Unpinned actions can change behavior without warning, or worse, be hijacked in a supply chain attack. Version tags give you reproducibility and safety. Actions are where GitHub's ecosystem truly shines. The community has already solved most of your automation problems. We've been talking about the runner as though it's obvious. Let's make it concrete. A runner is a virtual machine, a full computer, running in the cloud that GitHub provisions specifically for your job. The moment GitHub Actions picks up your job from the queue, it provisions a fresh VM, boots it up, and hands it to your workflow. When your job is done, that VM is destroyed. Gone. The next job that runs on Ubuntu latest gets a completely different, completely clean machine. This fresh per job model is one of the most underrated features of GitHub Actions. It means you never have to worry about leftover state from a previous run. No accumulated temp files. No conflicting dependencies. No, but it worked on CI last week, mysteries. Every run starts from 0. GitHub offers 3 hosted runner families. Ubuntu latest is by far the most popular. It's the fastest, cheapest, and comes pre-installed with an enormous toolkit: Docker, Node, Python, Java, Go, Git, and hundreds more. Windows latest gives you a Windows Server environment with PowerShell. macOS latest is essential for iOS and macOS development. It's the only way to run Xcode in a cloud CI system. If your company has compliance requirements or needs access to private network resources, you can set up self-hosted runners, your own machines that register with GitHub and pick up jobs just like hosted runners do. Every workflow run automatically gets a secret credential created for it by GitHub. It's called GitHub_token, and it's one of those features that seems small but solves a massive headache. Before GitHub_token, if your CI pipeline needed to push back to your repo, say, to commit a generated changelog or create a release, you had to manually create a personal access token, store it as a secret, manage its expiration, and worry about what happens if the person who created it leaves the company. Painful. Now, GitHub creates a token automatically when each workflow run starts. It's scoped exclusively to your repository. It expires the moment your workflow finishes. You access it with the expression secrets.github_token. No setup. No rotation. No human-owned credentials in your automation. What can it do? By default, it has read access to your repository contents, metadata, and checks. It can trigger deployments. It can comment on pull requests. With appropriate permissions granted, it can create releases, push packages to GitHub packages, and even push commits back to your repo. The key word there is with appropriate permissions granted. By default, GitHub is deliberately conservative. The token has read access to most things and write access only where specifically needed. You use the permissions key in your workflow to explicitly grant write access where your pipeline actually needs it. Security through explicit configuration. Almost every build tool, test framework, and deployment script in existence is configured through environment variables. Node_env. Database_URL. API_key. They're the universal configuration mechanism. GitHub Actions gives you a layered system for setting environment variables, 3 levels, each one narrower than the last. At the top is the workflow level. Variables defined here are available to every job and every step in the entire workflow. Perfect for things like the app name, the environment name, or any configuration that's truly global. Below that is the job level. Variables here are available to every step in that specific job, but not to other jobs. Good for job-specific configuration like the test database host or the deployment target for that job. At the bottom is the step level. Variables here exist only for that single step's execution. When the step ends, they're gone. The precedence rule is simple: narrower scope always wins. If you set node_env to production at the workflow level but override it to test in a specific step, that step runs with node_env as test. All other steps see production. This layering is incredibly powerful for test environments. You can set production configuration globally but selectively override individual values in your test steps without duplicating everything. One source of truth, with targeted overrides exactly where you need them. Alright. We have all 5 concepts under our belt, plus actions, runners, tokens, contexts, and data passing. Now let's watch them all work together in one complete story. You type git push. Your commits travel over the internet and land on GitHub's Git servers. GitHub's backend records the push, identifies the repository, and fires an internal push event. The Actions API immediately wakes up. It scans the repositories.github/workflows/folder and looks for workflow files that listen to the push trigger. For each matching workflow, it evaluates whether the push target branch matches the configured branch filters. Matching workflows proceed, non-matching ones are ignored. For each matching workflow, GitHub creates a workflow run, a record you can see in the Actions tab. Each job in the workflow is evaluated for readiness. Jobs with no needs dependencies are immediately queued. Jobs with dependencies wait until their dependencies resolve. Meanwhile, somewhere in GitHub's infrastructure, a fleet of runner VMs is polling the Actions job queue. A free runner picks up a queued job. It claims the job, receives the workflow YAML and event payload, and begins execution. Clone the repo, restore caches, execute steps one by one, stream logs back to GitHub, save caches, report final status. The whole process, from your git push to the first step executing, typically takes under 30 seconds. The architecture is designed for speed. Security in CI/CD pipelines follows the same principle as security everywhere else: least privilege. Only grant what is actually needed. Nothing more. In GitHub Actions, the permissions key is your mechanism for enforcing this principle on the GitHub_token. Here's the security calculus. Your workflow uses community actions, code written by third parties and pulled from the internet. Some of those actions may have vulnerabilities. Some may even be malicious. If your workflow's token has write access to everything, a compromised action can push code to your repo, create releases, modify branch protection. The blast radius is enormous. The defense is simple but powerful. At the top of your workflow, set permissions, an empty map. This revokes all default permissions. Then, at the individual job level, grant exactly the permissions that specific job needs and nothing more. A release job needs contents, write to create the release. A container job needs packages, write to push images. A job that reads code from the repository needs contents, read. A job using OIDC to authenticate to AWS or GCP needs ID token, write. By being explicit at the job level, you've built blast radius containment directly into your pipeline architecture. Even if a malicious action runs inside the release job, it cannot touch your packages. Even if the test job is compromised, it cannot push code. Defense in depth, expressed in YAML. As your GitHub Actions usage matures, you'll start seeing duplication. 20 different repositories all checking out code, setting up node, running the same linter. You copy-paste the same 15-line setup block everywhere. Then the linter version changes and you have to update 20 repos. There has to be a better way. GitHub gives you two tools for sharing automation logic. They look similar but operate at fundamentally different levels. A composite action bundles multiple steps into a single reusable unit. You reference it with uses just like any other action, but it's your own code. It runs inside the calling jobs runner, sharing the same workspace, the same environment. It's perfect for setup routines, checkout, install dependencies, configure tooling. The limitation is that a composite action cannot define its own jobs, cannot have its own triggers, and cannot run on a separate machine. A reusable workflow is a full workflow called from another workflow using uses. It spins up its own runner, its own jobs. It's an entirely separate execution environment. You pass inputs and secrets explicitly. It can even use matrix strategies internally. This is for sharing entire pipeline patterns, the full build test deploy sequence that every team in your organization should follow. The decision tree is simple. If you're sharing steps that belong inside a single job, use a composite action. If you're sharing an entire multi-job pipeline pattern that needs its own execution environment, use a reusable workflow. And here we are, the moment of truth. Time to test whether the architecture has truly clicked. You have a workflow with two jobs. Job A runs your test suite. Job B deploys the application. Job B is configured with needs, Job A. The question is deceptively simple: when does Job B start? Let's think through the wrong answers first. Does it start immediately, in parallel with Job A? No. That would be the behavior without needs, but you've explicitly declared a dependency. Does it start while Job A is running, before Job A finishes? No. The whole point of needs is to wait for completion. Does it run as a fallback when Job A fails? Absolutely not. That's the opposite of how it works. The correct answer: Job B starts only after Job A completes successfully. Both conditions matter. Job A must complete, and it must succeed. If Job A fails even one failing test, Job B is skipped entirely. Not failed. Skipped. GitHub knows you never want to deploy code that didn't pass your tests, so it skips the deploy gracefully. This behavior is the entire safety guarantee of sequential pipeline stages. Tests gate deploys. Build gates publish. Security scan gates release. The needs key is how you encode these real-world constraints directly into your pipeline architecture. You now have the full mental model of GitHub Actions. Events trigger workflows. Workflows define jobs. Jobs run on runners. Steps do the work. And needs keeps the whole chain honest.